Hey everybody, Husky back again, and we are moving on to the next challenge that I wrote for the Huntress October 2023 Capture the Flag competition. So next up, another one that was absolutely amazing to watch unfold in the Discord when it went down was BlackCat, all right? So I want to point out that this one is marked as easy. And although, caveat here, the difficulties are always subjective based on who is performing the challenge, I want to show you why I made this one easy and hopefully explain a little bit about just the approach to how to solve this one. So let's go ahead and get started, and we can just get this right to the desktop. I think we could do outfile blackcat.7zip. And I'm getting this because Google Chrome a lot of the time blocks the downloads from the ctf.games site. That's because it's a byproduct of us hosting a lot of malware challenges or emulated malware challenges. Well, the domain reputation for .ctf.games is absolutely abysmal, so that is the reason why. But anyway, let's see if we can open this up in 7-zip. And there we go. So let's extract to the desktop and let's get moving. Standard password of infected. You know the deal. All right, let's get working on it. So first things first, let's see what we're working with. We've got note.png, and when you open this up, you get a fantastic little ransomware note featuring my real-life actual cat, Cosmo. And we've got a ransomware note from the BlackCat ransomware group. Your files are ours. That's right, et cetera, et cetera. Paste the Bitcoin. You know the deal on that one. Also, if you'd like to fill out the survey to let us know how we're doing, we'd love to hear your feedback. That's very considerate. I like ransomware groups that want to improve their customer service skills. So anyway, the other files in this challenge are decryptmyfiles.exe and victim files. So let's go in and check out victim files. Of course, we've got our victim files here. If we try to open these up, we've got scrambled, garbled junk here. We've got bliss, windows xp.png.encry. We've got the Huntress Labs logo. We've got my favorite rock, the entire text of Hamlet, and the flag itself. All right, so these files are certainly encrypted. And if we want to just check another one here, we can open up the entire text of Hamlet. And yeah, this is all scrambled. I mean, we're not going to be able to just read and get any information out of this. Or are we? A little spoiler for later. But anyway, let's take a look at decryptmyfiles.exe. So if we go ahead and run decryptmyfiles.exe, we get the ASCII art here, and then it says enter the ransomware key to decrypt your files. So we have the idea of the challenge is that we would have to pay them, and then they would give us the key, and we would input the key here. But because this is a CTF challenge, we know that that's not going to be the case. So we're not going to actually pay a ransom. We need to figure out how to do this without paying the ransom, in air quotes, of course. So if we try to enter a key in here, let's just put an A. It says the key is too small. All right. So if we then fuzz a little bit, so that's 1, 2, 3, 4, 5, 6, 7, 8. We need to fuzz to see what the minimum key length is. And in this case, if we put in 8 A's, that ends up being the minimum key length. So we have at least a minimum key length of 8 that we need to figure out. And when we put in a random arbitrary key like this, we're going to get the decryption completed for each of these files. But if we go back into the victim files directory and we look at, oh, great, we've got flag.text.decrypt right here, right? If we open this up, unfortunately, that's not the case. We still have a very, scrambled junk kind of thing going on here. Pong. That's so funny. Anyway, totally random. Did not plan on that happening. Anyway. Okay, so how do we figure out where to go from here? So you got to think about the pieces of the puzzle here. We have the actual decryptor utility. This is a Golang binary, and one of the approaches, I think a lot of people thought the obvious approach here was going to be reverse engineer the decryptor. And I can totally understand why you would go after that. At the end of the day, this is a Golang binary, so the reverse engineering is a little bit more involved. And what really ends up happening is that you only really find one fact that you could find elsewhere from looking at the different files in here. So that is to say, reverse engineering the decryptor is one possible solution that'll get you a little bit further in the solution here, but that wasn't really the best way to go about this. The best way to go about this is to look closely at the other files in this encrypted directory. Okay, so let's go ahead and launch our hex editor, HXD. So this is our Hex Viewer hex editor, and the idea here is that we want to take a keen look at the different files that have been encrypted and see if we can identify any consistencies or anything that looks kind of out of place. So if we go to victim files and we take any of the victim files here, we can take a look at the bytes of them. So the first one, I think the quickest solution, the easiest solution and approach here would be to look at these two right here. Bliss Windows XP.png, the encrypted file, and then the Huntress logo .png. Now, critically, these are both PNG files, and critically, they've both been encrypted by the program. And so we can take a look and see if there's any consistencies between these things. So I'm going to actually put this one to the side, and let's see if we can open up another hex editor here, or maybe we could do like new window. Yep, and then we can open up this one over here. So let's open up the Huntress logo as well. So we've now got, we can actually get rid of this. We've now got Bliss Windows XP.png. That's the background of Windows XP if you're old like me. And the Huntress Labs logo. Now, if we flip between these two on the tabs, one thing stands out immediately, and that is the first 8 bytes, or maybe even more than that, but specifically the first 8 bytes of both of these files are the same. EA3F3D2A, EA3F3D2A, and then it goes on 62687563, 62687563. The first 8 bytes of both of these files are the same. They're both encrypted, and the first 8 bytes are both the same. And these are both the same file type. Now, this is when we go to Google and we look up PNG magic bytes. And so if we go to the list of files signatures, now Windows identifies files by their extension, but the construction of the file, the actual bytes of the file, need to have a magic byte header here. So let's just quick search for PNG. There it is. Okay. So any image encoded in the PNG format will have these bytes as the start. And we know that this is a known value, all right? So we've got the magic bytes, wherever they just went. Let me go find those again. We've got the magic bytes of PNG 8950-4E47-0D-0A-1A-0A. And we've got the known 8-byte headers of 2 encrypted PNG files. So this is now a known plain text attack against encryption. Now, the addition of, if you went in and reverse engineered the decryptor, you find out that all it's doing is using an 8-byte key to XOR decrypt files. So you pass it in the XOR key, and it XORs files in 8-byte chunks until it's done with that. So if we put all of that together, we can, even if we don't reverse engineer the decryptor, we can take a really good educated guess that the 8-byte file header on these 2 encrypted files are the same. So that means the same key was used to encrypt them. That means the same key will be used to decrypt them. And that means that we have known plain text and we have known ciphertext right here. And so now we're dealing with a simple XOR attack with known plain text against known ciphertext. And if you XOR the plain text with the XOR key, you get the ciphertext. But if you XOR a known plain text with the ciphertext, you get the key. And that's what we need to do. So I think that Python is probably the best, easiest way to solve this, but you could also kind of do this in CyberChef, any way that you want to approach this. But basically, you have to plug in the known plain text, you have to plug in the known ciphertext, and XOR those together, and you'll get the key. So we need our ciphertext, we need our known plain text, and we'll basically do a define XOR values, right? And then into this, we'll put in the ciphertext and the known plain text. And so our function will do basically, let's make a decrypted byte array. And then we will do for I in range len of the ciphertext. And really, those are both the same length, so it doesn't really matter there. And so this is our boilerplate. Like if you look this up on Rosetta Code or something like that, this is the boilerplate way to do a simple XOR. So we're doing decrypted byte. And then we're going to do equals the known plain text, and then of I, and then we're going to do the caret there, and that's going to be the XOR operator, XOR against the ciphertext, and then I mod len of the plain text, known plain text. So this is our boilerplate simple XOR algorithm right there. And then what we want to do is append that byte that we've XORed back into decrypted. So what we want to do is decrypted append, and then the decrypted byte There we go. And then at the end of all of this, we want to return decrypted. Return decrypted. So now, if we want to call main, we'll say in main, we're going to just XOR our, or well, we're going to say key equals XOR values of ciphertext and known plaintext. And then we're going to say print key. And we will see what that gets us. And the last thing that we have to put in are the ciphertext and the known plaintext. So we got to plug those values in. So in this case, known plaintext and ciphertext really come down to the following. We're going to plug in our hex encoded values of the first 8 bytes of both of these, or really just the first 8 bytes that are in the PNG file. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. We'll copy that. And all we've got to do is paste this in, and then we just got to do some quick Python byte formatting here. And we're going to pull the known plaintext right from our list of well-known, well-defined file headers, right? And so we do basically the same thing here. So we byte string, and all we got to do is throw the /x in there as well. Copy, and we... Okay, great. So let's save, and I'll just throw this on the desktop. It doesn't really, we'll call this xor.py, and then let's open up a terminal and see what we got. And we will Python xor.py. Oh, I'm sorry. I forgot to call main, of course. Oh, man. You never, like, it's funny. You never stop making those little mistakes. Excuse me. If name equals main. You never stop making those simple little mistakes, and that's okay, because it's all about the learning. It's all about, you know, just having fun with it. Okay, fantastic. So we got our ciphertext, we got our known plaintext, and we XORed those two together, and we've got the byte array of Cosmo Boy. All right, so if we take this now, and we go right back over to the desktop and we run decryptmyfiles.exe. We paste in Cosmo Boy, and we have just thwarted the infamous BlackCat ransomware group because we now have our files safe and sound. And so we've got the flag there, and we can go over and check out Bliss. And of course, if we open this up in Notepad, we're not going to see much. But if we open this up with, you know, any of the other ones here, actually, I probably need to just set this to be a PNG. I think that would be fine. And if we open this up in our photo viewer, then we should see the awesome background of Windows XP any minute now. There we go. Beautiful. All right, that's BlackCat. That was a known plaintext against a weak XOR encryption routine. And I hope you enjoyed that. That's the walkthrough.